Hi, I'm Alex Dzewaltowski. I'm a PhD student at the Department of Biomechanics at the University of Nebraska, Omaha, and I'll be talking to you guys about a neuromuscular model or a simulation for walking. So first off, why do you want to do simulation? Usually it's to substitute or supplement experimental data collection. We're most interested in metabolic rate because it's a key indicator of performance for assistive device design or rehabilitation strategies. But those assistive devices and rehabilitation strategies are designed for clinical populations who are frequently unable to walk for a sufficient duration to actually measure this key indicator of performance. So that's where we're kind of turning to simulations to maybe address or assist that problem. We're also just generally interested in developing alternative estimation methods of metabolic rate to maybe increase the attainable resolution to within stride, maybe even more so inform these assistive device design decisions. Okay, so here we're going to look at our lab's previous work where we were able to show reductions in metabolic rate with assistance at the center of mass. So here we have the lead author on that paper currently under review, Dr. Antonellis, who had received assistance at the center of mass. And here's where we're headed, this neuromuscular model with assistance applied at its center of mass. And we're kind of hoping that these reductions in experimental metabolic rate are reasonably close to our modeled reductions in metabolic rate so that we now have a framework to kind of build off of for these informed decisions in assistive devices and further development of estimation methods. So Dr. Song, who is a collaborator on this project, created this really cool neuromuscular model with Dr. Geyer. It uses 9 lower limb muscle groups and implements a muscle reflex controls hierarchy that discovers a strategy for walking. So what we want to really make clear is we don't give it any experimental data, as we kind of implied earlier. We don't need to provide motion capture. We don't need EMG information. It's truly just a walking model that you're tuning some parameters of how the muscles contract in order to achieve a strategy for walking. So this is able to handle a very dynamic environment, one that we actually present it with these assistant forces at the center of mass. And so an initial parameter selection might look like this. You see him kind of stumbling. He's not necessarily able to walk in an even pace, maintain a certain walking velocity, and ultimately actually falls down. And so we use an algorithm called covariance matrix adaptation evolution strategy, or CMA-ES. And this allows us to run thousands of iterations, but rather than the maybe hundreds and hundreds of thousands of iterations that you really need, it's a better guessing strategy, it will say, that leverages previous iterations, successes, or values on the cost function to inform future tuning of those parameters to achieve a walking strategy. So we start with an initial control parameter set and an estimated standard deviation for that. Of unassisted walking, we apply then assistance at that center of mass and essentially let CMA run to find a solution. So after 8,000 iterations, as I said, we discover a strategy that resembles actual walking. And so that might look a bit more like this. So we have assistance at the center of mass, and we see this pretty even-paced walking strategy. We're no longer kind of stumbling back and forth, and our stride length is fairly consistent. And we're really pinning in a specific walking speed for this at 1.25 meters per second. Now, the benefits of this kind of system is that we now have complete information, right? So we have muscle contractile dynamics, which means we now can leverage this metabolic rate estimation method created by Umberger that uses estimated contractile dynamics. And when we put our information into this metabolic cost model, we can make comparisons to our original experimental data collection. So over 35 different assistive conditions with that at that center of mass, we see our model approximation compared to unassisted walking of our model to the experimental reductions of an average 10 participants. What you see is a dashed line, which represents a perfect correlation between the tether condition reduction in metabolic rate of our model compared to the experimental reduction in metabolic rate. So as you can obviously see, it's not perfect, but these gray lines indicate the standard deviation of our actual experimental collection. So we're well within a single standard deviation for the majority of our data, our simulated data for metabolic rate. So this is really exciting to us. This is a very cool thing that without any other information, we apply this dynamic walking environment, we're able to get reasonably close estimations of metabolic rate or estimated predictions in this dynamic framework. So with that, we're looking again to hopefully supplement and look at simulating different clinical populations to maybe better create assistive devices or rehabilitation strategies before even needing to do any sort of testing in those populations. And hopefully that will relate to better clinical outcomes. But we're also interested in creating new metabolic estimation methods. Again, using this very complete set of knowledge and creating a solution set for metabolic rate. Because in essence, now we have complete information and better outcome measurements of metabolic rate in a much more consistent fashion. And so hopefully that'll lead to some really cool things in the future. Okay, with that, I just thank my lab. There's the individuals who collected the experimental data used for this project.